Psychophysiology. Behavioral studies have taught us important information about what infants and children know about the world. Research on behavior alone, however, could not tell scientists how brain development or biological changes impact behavior. For this reason, researchers may also record psychophysiological data, such as measures of heart rate, hormone levels, or brain activity. These measures may be recorded by themselves or in combination with behavioral data to understand the bi-directional relations between biology and behavior. One manner of understanding associations between brain development and behavioral advances is through the recording of event-related potentials, or ERPs. ERPs are recorded by fitting a research participant with a stretchy cap that contains many small sensors or electrodes. The electrodes record tiny electrical currents on the scalp of the participant in response to the presentation of a particular stimuli, such as a picture or a sound. The recorded responses are then amplified thousands of times using specialized equipment so that they look like squiggly lines with peaks and valleys. Some of these brain responses have been linked to psychological phenomena. For example, researchers have identified a negative peak in the recorded waveform that they have called the N170. This peak is named in this way because it is negative, hence the N, and because it occurs about 140 to 170 milliseconds after the stimulus is presented, hence 170, the N170. This peak is particularly sensitive to the presentation of faces, as it is commonly more negative when participants are presented with photographs of faces rather than with photographs of objects. In this way, researchers are able to identify brain activity associated with real-world thinking and behavior. The use of ERPs has provided important insight as to how infants and children understand the world around them. In one study, researchers examined face and object processing in children with autism spectrum disorders, those with developmental delays, and those who were typically developing. The children wore electrode caps and had their brain activity recorded as they watched still photographs of faces of their mother or a stranger, and objects, including those that were familiar or unfamiliar. The researchers examined differences in face and object processing by group by observing the component of the brainwave that they call the PR N170. This is because it's believed to be a precursor to the adult N170, hence the PR. Their results showed that the height of the PR N170 peak, commonly known as the amplitude, did not differ when faces or objects were presented to typically developing children. When considering children with autism, however, the peaks were higher when objects were presented relative to when faces were shown. Differences were also found in how long it took the brain to reach the negative peak, which is called the latency of the response. Whereas the peak was reached more quickly when typically developing children were presented faces relative to objects, the opposite was true for children with autism. These findings suggest that children with autism are in some way processing faces differently than typically developing children. If you would like to read more about this research study, it is published by Webb, Dawson, Bernier, and Panagiotis. 2006. Research Methods in Developmental Psychology by Angela Lukowski and Helen Milojevic is licensed under a Creative Commons Attribution, Non-Commercial, Share-alike 4.0 international license.